Age 69, Santiago Calatrava is a Spanish structural engineer, architect, and sculptor. I chose Santiago for two reasons. Firstly, I believe he demonstrates a truly blended approach between architecture and engineering, having trained in both fields. He's famous for his biomimicry in architecture, creating truly unique structures. Secondly, he's extremely polarising and controversial within the industry, hailed as a visionary by many and heavily criticised by others due to inefficient material use and lack of consideration for constructability. A new roof would transform the existing 75,000 capacity Spiros Louis Stadium into the Athens Olympic Stadium. The roof would be supported by two distinctive long-spanning arches and two lower torsion tubes. Originally constructed in 1982, the brief was modernisation and harmonisation of the existing structure with the surrounding complex. The focus was to incorporate design excellence to capture the hearts and the minds of the public and showcase the transformation of a small developing Greece into a dynamic modern European state. Two 332-metre long upper arches go into compression to carry the majority of the roof load through steel main and secondary cables acting in tension. The arches are helped by two 316-metre long torsion tubes. Steel girders hold polycarbonate panels and are supported by the secondary cables and torsion tube. The arches and tubes meet the ground at four 250-ton steel support chutes, which provide horizontal thrust and transfer vertical loads to the concrete board piles. The two halves of the roof were built 70 metres away from the existing stadium using strand jack towers and were pulled together into place along 4 tracks just days before the first event. The tracks were built on temporary foundation beams and each of the 4 shoe supports had been constructed on Teflon skids. Long-stroke hydraulic pulling cylinders were used to reduce the number of steps in the movement and therefore reduce construction stresses induced within the structure by repeated acceleration and deceleration. The measured coefficient of friction was as low as 3% during the sliding. The first driver was to create an illustrious venue. The Greek government wanted a major addition to the Athenian skyline, a statement of the city's entry into the 21st century and a lasting impression of a successful games. For this reason, the roof had both political and psychological meaning and needed to reach the public in a mental and visual way. Drawing inspiration from his previous work, such as the Zubi-Zuri Bridge in Bilbao, Calatrava chose slender, circular hollow section arches as the main structural system. The second driver was an efficient structure symbolic of the games. Calatrava's explanation for the choice of arches spanning in the long dimension of the stadium is that they coincide and reflect the track and field athletes' efforts along the long dimension of the stadium. For example, long jump, the 100 metres, javelin and discus. The arches are therefore in harmony with the athletes. There are no arches in the short dimension which supports this notion. Long-spanning arches are also more structurally efficient than alternatives such as cantilever roofs or long-spanning truss beam roofs. Cradle-to-gate embodied carbon was focused on for this project, as reduction enhancements are structural and therefore affect the A1 to A3 scope more directly. Carbon footprint was calculated using geometry and information found in reports, drawings and judgment of precedent images. Embodied CO2 equivalent factors were obtained from the inventory of carbon and energy and found the total embodied carbon to be 37,180 tonnes of CO2 equivalent. This was dominated by the self-weight of the steel roof structure, accounting for 76% of the total. Wembley Stadium's lattice arch has a mass of 1,490 tonnes. However, if it was a circular hollow section with a 150mm thickness, it would have a mass of 6,070 tonnes. Therefore, the decision to make the arch a truss lattice resulted in a 70.5% reduction in mass. Calatrava reportedly dismissed the truss arch as he felt it would look too industrial. However, I believe it would look more lightweight and convey the same architectural drivers. Due to the differing dimensions of the arches, a conservative mass reduction of 50% is assumed for the upper arches and torsional tubes. Calatrava's team were forced to increase the arch and torsion tube section sizes by 30% from their original 2.5 and 3 metre diameters following a study on seismic critical load cases. Poor ground conditions were also found at a depth in late site investigation, causing an increase in pile length by 10 metres to provide sufficient bearing capacity and horizontal thrust resistance. By inclining the piles at the foundations, horizontal thrust could be increased within the arches. Studies have also found that by inclining pile foundations, earthquake resistance of bridge foundations can be improved. Implementing this with the lattice arch, a conservative additional reduction in mass of 15% is assumed, meaning the total estimated reduction in mass of the upper arches and torsion tubes is 65%. ETFE could be used instead of the polycarbonate panels as they are 20 times less dense and have lower embodied carbon per unit mass. The result is an extreme reduction of 8.7% of the total embodied carbon of the structure. The total embodied carbon with structural enhancements is 23,880 tonnes of CO2 equivalent, meaning a reduction of 36%.